This slide is important because what it does is it addresses those basics of our common reaction types. So you need to be able to look at any given reaction with a bunch of different drawings or structures on it and be able to identify what big things have changed so that you can classify the reaction type. Once you know the reaction type, you can potentially start to zero in both towards reagents and towards mechanisms. So you have to be able to recognize these certain patterns. I'll talk through them because they're important enough to address. So if we start all the way at the top with acids and bases, if we look at our reactants to our products, what we should note is that the only thing that has really changed is where that hydrogen is connected. It's either connected to the oxygen or connected to the nitrogen. Because we've changed just the location of a hydrogen ion, in particular an H+, we'll reference this as an acid base. Okay, so that big deal is that we're doing the transfer of hydronium, or not hydronium, a hydrogen ion. There will be cases where you might see the transfer of an H- that is not specifically considered acid base, though those could show acid base characteristics, but it's not acid base. So we're looking very particularly at the transfer of a proton, so just a hydrogen. When we move to the substitution reaction and we evaluate again beginning to end, one of the things that you'll notice is that almost always in the substitution our reagent starts to move above the arrow as opposed to being in front of the arrow. So that is a big kind of shift in change. Sometimes your reactions will show them above, sometimes they won't. Just be aware of that. When we go through and look at the pattern, what we should be noticing is that a species that had electrons is now connecting to our starting structure. And at the same time that that connection is made, another piece moves or is replaced. So you could almost look at this as like a double replacement reaction, which I'm really hesitant to call it that, but it looks very similar to the double replacements that you might remember from Gen Chem. Okay, one of the things that makes it more challenging is in Gen Chem you were looking at ionic formulas, which made it easier to identify that exchange. Here we're looking at structures. The structures can make that replacement look a lot more confusing, and it doesn't always replace. Okay, for instance out here, for instance with our leaving group, sometimes it'll hook back up with the metal, sometimes it won't. We don't do a good job addressing what happens to the leaving group, which can make it difficult to see that double replacement type situation. In an elimination reaction, the big tip-off that you see there is the formation of a pi bond. Okay, that is your number one big thing. Okay, seeing the presence of that pi bond. Part of that is also the loss of two sigma bonds. Those two sigma bonds are very difficult to see. One is usually obvious. The other one is less obvious. It's a hydrogen, an implied hydrogen that is lost from that. So if you're looking at a reaction and you see a pi bond on the product side, that is very likely to be an elimination. The reverse of an elimination is the loss of a pi bond. So we're looking for that pi bond on the reactant side and then it's somehow disappearing. It's usually resulting in the formation of two new sigma bonds. Again, their content of what those sigma bonds are may vary, but its big tip-off is that pi bond loss. And then the last one is radicals, and radicals are just a mess. Big tip-offs for that is things like elemental bromine, elemental chlorine, ROR, and we'll address what these things mean much later in the semester, light and sometimes heat. Okay, so light and ROR are almost guaranteed tip-offs that you're looking at a radical mechanism. To a lesser extent Br2, to a lesser extent Cl2, not a useful radical, which is why we don't see it, and to a much lesser extent heat. Okay, but what's happening within a radical is you're moving single electrons. The only time you're going to really see a single electron move is if you're being shown a mechanism. So if you're being shown the reaction, that doesn't really help. Okay, but if you see single electrons or unpaired electrons or half-headed arrows, a radical is a really big tip-off that's what you're looking at. Okay, so in this next unit, where we're going to focus is in our substitution and our elimination reactions. So students have in the past requested they get these big summaries ahead of time. So here's our big summaries of the big pieces that you need to know and be able to identify and find for both our substitution and our elimination reactions. So within each of these reactions, and since we were color coding it before, our reactions being in black, we have two different types of mechanisms. Okay, those mechanisms change the end results. Okay, and they each have slightly different aspects behind them that change how they function and what they produce and all that fun stuff. Okay, so what we're seeing on this slide is those major summary things that help us kind of get tip-offs of what we're looking at. So some of that is rate. If you're given a rate law, what would your rate law look like for an SN1? Well, it's just dependent on the alkyl halide. For an SN2, it's dependent on the alkyl halide and the nucleophile. So it gives us some information on what we'd be looking at if we were given just an explicit rate law. Yes, that's 152. Yes, we'll see a summary of that information later. Substrates. You'll be given reactions with a whole bunch of structures. So once you've identified where the chemistry is happening, you need to be able to classify that. The easiest classification we'll come up with is tertiary, secondary, and primary. So if you can classify your substrate and you see that it's tertiary, that's a hint that it's not SN2, it could be an SN1. Nucleophile strength. When identifying your nucleophile, if it's weak or strong, that pushes one mechanism over another. Solvent, same kind of deal, protic versus aprotic. Same kind of aspect goes with your eliminations. We're looking at those major kind of bulk categorizations that allow us to evaluate and try and determine differences to decide which mechanism is predominantly happening. Okay, that's the point in the driver behind this slide. It summarizes those big pieces. You would now have to apply those over the top of the structures and the reactions you're looking at. There are complications within both of these, or all four of these technically. You'll notice that we're seeing reference to stereochemistry. So stereochemistry pops up with SN1 and we see a loss of it in quotes. We'll address that. Okay. And SN2 we get inversion. So if it's R it becomes S. If it's S it becomes R. So these are things that you need to be aware of. So once you've gone through the rules of looking at your reaction and saying, oh, it's an SN1, well, then you would apply the complications to that. If it is SN1, then that means the product I draw has to be racemic, which ultimately means I have two products. Okay. If I know it's SN1, I know I'm also expected to predict that an E1 elimination is going to be running simultaneously. Okay, so I have to be aware of those complications. So we're using the previous slide to decide which mechanism is the primary one, and then we move to the the complications to say what are the specifics of the product that I'm going to be getting, what are characteristics of it that are going to allow me to drive how it moves through. Okay, so that's what these big kind of summary slides are. They'll show up again and again. We've got probably 10 summary slides throughout this slide deck that you should be looking at and trying to memorize. So let's start with substitution and evaluate. So when we go through and look at this reaction, we're trying to decide what changed. So first and foremost, we should see that that carbon has changed characteristics. It was bound to an iodine, and in the end, it was bound to a chloride. Okay, so we know that there's a change there. So now the question comes about, well, how did that change happen? Okay, I know for sure that I have to form a bond between the chloride and the iodine, or the chloride and the carbon, and I'm also going to have to break a bond between the iodine and the carbon. Okay, before we start pushing into those mechanisms, it's useful to think about how these things could have come about. Okay, so we really only have two things that are happening. We're breaking one bond and we're making another bond. Okay, so with only two options, how many possible ways can we get this to stack out? Okay, so the idea here is we're thinking about two coins. We can flip and get heads, or we can flip and get tails. Or we could flip and get tails and flip and get heads. Okay, or heads and heads, tails and tails. So what we're trying to do is think of those possible outcomes. So come up with a plan here, okay, and I'll give you a hint. There are actually only 3 possible combinations. And think about how we could possibly make and break these bonds. Okay, so let's go ahead and say, well, how about we make and break at the exact same time? Okay, so make and break. Okay, so these are now happening at the exact same instant, so simultaneously. Okay, what other options are there? Well, how about we make the bond first, then, so notice the change in language, we're going from an and to a then break in a subsequent step. Okay, and hopefully that sets us up with the last one. We could break our bond first, then we could make our bond. Okay, and what does this mean for us? Okay, so what this is establishing is how many mechanistic steps are involved in our overall reaction. Okay, for type 1 and type 3, we're saying those are happening in 2 steps. Okay, that's why we have that then. That's what that then is tipping us off at. Okay, 2 mechanistic steps. Whereas the type 2 one in the middle is all happening at once, so this is 1 step. Okay? So this gives us 3 possible options. We already hit our summary slide, and the summary slide said it was SN1 and SN2, not 3. So is one of these impossible to happen? Okay? If I broke the bond first, whoop, wrong eraser. If I broke the bond first, then that bond isn't there. Okay? So I would have the iodine floating off. So a question could come about, how did the iodine float off? Did the iodine take the electrons, or did the carbon take the electrons from the iodine? Okay, well, how would we predict that? That's differences in electronegativity. Since iodine is more electronegative, we would expect the iodine to take the electrons, leaving behind a carbocation. Okay? The carbocation is not particularly stable, but it's possible. It's not an invalid structure, it's just not a good one. Okay? Then I could make a bond. Okay, so that works. We may be forming something that we don't like. Okay, that breaking generates a carbocation, and we may not like that, but it's at least not invalid. Okay, the other option is we make and break at the exact same instant. Okay, so we're starting to make a 5th bond. Remember, there's a hydrogen there. We're making a 5th bond to that chlorine. That could become problematic, except we're breaking the iodine at the exact same instant. So we never really go beyond 4 bonds. We're just maintaining that octet through the whole time. So making and breaking could work. What about make and then break? Well, if we make the bond first, well, now we have to have a carbon with 5 bonds, or 10 electrons around it. Well, that is not possible. That gets us a pentavalent carbon. Pentavalent carbons are not allowed. Valent. Which then means that last mechanism doesn't exist. Okay, this is pretty cool because this now sets us up with the 2 mechanistic steps, okay, or the possibilities. What we're trying to think about is just how does this happen? Once we know how it happens, we can now look at the repercussions of what does that mean if those steps happen. Okay, so elimination, similar idea. We want to do the same thing. Okay, in this case, we're still breaking a bond. Okay, that carbon X bond is getting broken. And I don't remember what color I used, so we'll just say red. Okay, so that bond is broken. What bond did I make? Well, the bond that I made was making a pi bond. Okay, how did that pi bond happen? Well, I broke also the bond with the hydrogen and then I could make that pi bond. Okay? The problem with that is we now have 3 different things going on, and that can make things a little bit more challenging to evaluate. So what I would argue you should do is try to simplify this a little bit. Instead of it being 3 things, let's see if we can change this. Instead of this being a carbon with a pi bond, let's draw the resonance structure, where we have the carbocation at one point and the anion at the other. So the electrons went that direction. Okay? Since this is a resonance contributor, it doesn't have to be a good one, since this is a resonance contributor, I could just as easily look at the formation from my starting material to that structure instead. And if I do that, what I'm actually noticing is that it's not 3 things happening, it's only 2. I'm breaking 2 bonds. Okay? And that's it. I'm breaking the carbon-hydrogen bond, so we'll call that one 1, and I'm breaking the carbon-X bond, and we'll call that 2. So with those 2 things, it's now again back to the drawing board of how does this possibly happen. Okay? So same concept, we could go through and look at all these possibilities. Okay? We do everything at once, break simultaneously. Okay? You may notice a pattern that my simultaneous reactions are always being affiliated in this number 2. Okay? That isn't just random and arbitrary, I intentionally picked that. Okay? Or I could break the X bond, then break the H bond, or I could break the H bond, then break the X bond. Okay? The eliminations become a little bit trickier because really there are 3 possible options. Okay? But we do get a little bit of a break here in step 3. Step 3 is very unlikely to happen. So now the question would become, why is it unlikely to break H, then break X? Okay, well, maybe the flip will help us out. Why would it be likely to break X? Okay, well, X is supposed to represent, say, a halogen. So let's make that chloride. Why would I expect that bond to be easier to break or easy to break? Well, there's a large difference in electronegativity. Chlorine, being more electronegative than the carbon, is willing to break that structure or come off of that structure. Okay? That does again form that carbocation. Just put that on the back burner for the moment. Okay? We're going to form reactive species if we're going to run a reaction. Okay? So that difference in electronegativity allows that bond to break. What if I flip that and look to the carbon-hydrogen bond? Okay, is the carbon-hydrogen bond likely to break first? Well, there's no difference in electronegativity. If I'm going to predict which bond is more reactive, I'm going to predict the carbon-chloride bond, not the carbon-hydrogen bond. Okay, and it turns out that that's the case. There are ways that we can make that carbon-hydrogen bond break, but they're very difficult to do. Okay, and they ultimately end up moving through different mechanisms. And I think different mechanisms. Okay, so don't worry about that last one. We really only have 2 options again, break X, then break H, or break simultaneously. Okay, so slightly different system because we don't have that nucleophile. We're not making a new sigma bond. We're removing bonds altogether, or sigma bonds altogether. And so that's going to change some of those dynamics. Once we've identified those core tenets of what makes our mechanistic steps, we can now start to run reactions and change the substrate, change that carbon structure a little bit to see how we might predict things to affect the end result. Okay? And that's largely what Chapter 8 is about. Okay? We go through and say, okay, let's say this is an E1. What does that mean for products? What things are going to control and dictate that? Okay, so there's all of our systems. What we're now pushing to is what are those elementary mechanistic steps. We just addressed them and broke them all down. When we were looking at the SN1, okay, or the one type for our substitution, which we will later know as SN1, we said we broke a bond, there's heterolysis, and then we made a bond, there's coordination. Okay? In the 2 type for our substitution, it all happened at once. Okay? Simultaneous, there's our substitution 2 type. For our elimination, what happened in the case of our elimination? Well, we broke a bond, heterolysis, okay? And then we actually broke another bond, but while we broke that, we made a pi bond. Okay? So it wasn't just the breaking of a bond, it was also the formation of a pi bond. So it is breaking the bond and forming a pi bond. There's our elimination name coming in. So now the question is, what did we break to make the pi bond? In that case, we broke off H+. H+ best fits in the electrophile definition, not the nucleophile, because it's missing electrons. And so our E1, or our 1 type for our elimination, is going to be a heterolysis followed by an electrophile elimination. And notice that the 2 type for our elimination follows all at once, so again follows in that simultaneous category. There's the E2. Okay? So what we're trying to do is combine those pieces and understand how they come together and how they fit to generate the products that we see. Okay, so let's go through and take a look at our simultaneous mechanisms. Okay, the simultaneous, for me personally, are more difficult, but they're much more useful, and so because of that utility, you probably will see more questions for the 2 type mechanisms, and we'll look at that utility in the next chapter. So if we go through and look at each of these 2 reactions, we should be able to identify which one's which. We should be able to call it the top one is a substitution and the bottom one is an elimination. Okay? So what happened mechanistically? So I have to break the bond between the carbon and the bromine. So I'm going to show those electrons going towards the bromine. Why would they go towards the bromine? Well, bromine is more electronegative than the carbon. So those electrons should already be drifting that direction. Okay? What else has to happen? Well, I also have to form a bond between the nucleophile, or that attacking species. In this case, it's going to be the iodine. Okay? It needs to form a bond with that carbon as the bromine leaves. So to show that that's happening at once, I can take the arrow from my iodine with its electrons, and that sodium gets bothersome, and since it's a spectator, we can effectively erase it, and I can show the electrons coming from the iodine and now forming that bond. Okay, so one arrow is showing the bond formation because we're taking non-bonding electrons and aiming them at an atom. In the other case, we're showing bond breaking because we're taking the electrons from a bond and moving them to an atom. Okay? That's now an SN2 mechanism. Okay? If we move down to the elimination reaction, you'll notice that as I was talking through things, I started making some changes to the bottom structure. And that's because we probably wanted a more specific example. And we'll adjust and make it less specific here in a second so you can see where those origins are coming from. So again, it all needs to happen at once. I need the electrons coming out to the bromine, and then I also need to be making that pi bond. So where are those electrons coming from? One of the common misconceptions is they're coming from a hydrogen, and we're just doing this. Okay? The problem with that would be what? Well, let's draw on the rest of the atoms on my structure. If we draw this out, this would be a CH3 on my product side, H, H, and H. If we compare left to right, is this blue hydrogen disappearing from the structure? If anything, it's still connected. So we've erased the wrong hydrogen. And so what's happening with that misconception is that students are Jumping over the elimination is the loss of a hydrogen in a leaving group, so they just start deleting hydrogens. Okay? It has to be a very particular hydrogen. Okay? If we think about what's happening here, this carbon is losing electrons. Okay? To make that pi bond, we need to be gaining electrons from somewhere else. If I gain them from this hydrogen, there's no place for the electrons to go to make a pi bond. I have to remove those electrons from a hydrogen that is located one carbon away from where my leaving group left. Okay, that was a big mouthful of words. Okay, so we could reference the position where the leaving group is as the alpha position, and we can reference the position where the hydrogen was removed as the beta position, and we can now call this a beta elimination. So if you hear people refer to beta elimination, that's why they're calling it beta elimination. It's a hydrogen located one carbon from where the leaving group is located. If we look at our arrows, okay, the red arrow is very clearly starting at the bond going to the bromine. The bromine is taking those electrons with it. Okay? The result, if we drew that out, would be a forming positive charge on that carbon. Okay? And I say forming, and we'll see that why in a second. Take a look at the blue arrow. That blue arrow is starting at the bond, because that's where the electrons are, and those electrons are getting moved to, not to a carbon, but to the space in between atoms. It's getting moved to another bond. So what we're doing is laying electrons down right here. Okay? So remember how I said forming positive charge? It's forming because if that blue arrow is drawn correctly, there is no positive charge. Okay? And we go directly to forming the pi bond. Okay? In our initial analysis, we went through and said, well, what about that positive negative thing? That positive negative thing was to help us simplify our mechanism, to understand that we're really just breaking two bonds. Okay? It's not moving the electrons stepwise from bond to atom and atom to bond. Okay? We're simplifying it, streamlining it all into one simple mechanistic sequence. Okay? So in this case, we could now say we have the beta elimination. But in this case, you'll notice that I did nothing with the sodium hydroxide. Okay? So what's going on with that? Because if we look at our product, we don't have sodium hydroxide anymore, we have water. What caused that blue hydrogen to be removed? Well, it's losing electrons, so it would be positively charged. We could again erase the spectator sodium. The hydroxide is sharing the electrons with the hydrogen, okay, which then causes the electrons in the bond between the carbon and the hydrogen to move away from the hydrogen because it's already got too many electrons to make our pi bond. Okay? The result is that we form our new pi bond product and water as a secondary product. Okay? So that's a more kind of specific example. Where I've got that LG is a bit frustrating because I'm getting iPad updates, which then prevent me from actually drawing what that LG is supposed to be. So we could draw that in as BR. Okay? If we now clear that all away, so if you want it, write it down. If we clear that all away, you'll notice that the specifics I gave you were a lot more generic. Instead of it being bromide, it was LG. LG for leaving group, because it is the group that is taking electrons away from our structure. Base. The base just has a lone pair of electrons, because minimally a base will need that. You'll notice there's this M/H, because again, it's generic. If we make it M, how does that change the characteristics? Well, M is M for metal. That would then make this base strong because the sodium would no longer connect to it, and the electrons in that bond would be on there, and we'd have a negative charge. If instead of being metal, it was hydrogen, well, now that bond is a lot stronger, which then means the base becomes less negative. It becomes a weaker base. Okay, so what I'm trying to show in this system is as generic a system as possible so that we can see all the possible applications that could come out of it. Okay? When we go through and look at the end result, you'll notice again that we see some kind of weird connectivity between the base and the hydrogen and the metal, because it depends on what base you're getting used. Okay? So this is supposed to be showing generic aspects. If we move to the stepwise mechanism, okay, both SN1, or the one type for both the elimination and the substitution, begin with heterolysis. So in that heterolysis, we're breaking that bond to iodine. That iodine is taking the electrons away from the structure, so we could actually call that iodine a leaving group because it is leaving with the electrons. The result of that, something is definitely goofed on this. Yeah, something's all sorts of weird on that. Oh well. The result of that is that we would still have our carbon structure, but now the iodine, having taken the electrons away, becomes negatively charged. Almost everybody nails that one. What everybody seems to neglect and forget about would be that carbon lost electrons too and is now positively charged. Okay? Because it is positively charged, it needs to get stabilized somehow. What is that somehow? Well, if there is a nucleophile, i.e. something negative around in solution, that nucleophile can share electrons with that positive, making a sigma bond, and we get our substitution reaction. Okay, but that requires the presence of a nucleophile. Okay, when we looked at our abbreviation, it's SN, S for substitution, N for nucleophile, 1. Okay, and we'll address the 1 a little bit later too when we get into rates. Okay, but what if there is no nucleophile? If there's no nucleophile, where do I get the electrons to stabilize that positive charge? I'm going to have to find them within the structure. Where I will find them is in a carbon-hydrogen bond. And we'll break that carbon-hydrogen bond to do the elimination, and we'll have H plus floating around on its own. That bond is not an easy bond to break. Right? So how could I increase the odds of breaking it? Well, I could add in a base. That changes the mechanism. Okay? So the way to increase the odds of that breaking without changing the mechanism is typically to add something like heat. So heat will cause that bond to vibrate enough and then break it. Okay? The big issue, or the big difference to note with our SN1 and E1 versus our SN2 and E2 is, as I delete everything here, is the formation of this guy in the middle here. Okay? This carbocation now becomes the linchpin that differentiates SN1E1 from SN2 and E2. That carbocation is an intermediate, and we would see that appear in our energy diagrams if we were to draw out a mechanism, okay, for our energy diagram. So usually we get this kind of question: do we care what the mechanism is? Okay, and my argument is almost always on the philosophical end. Yes, we always care what the mechanism is. Okay, because the more I understand about how and why it works, the more likely I can apply that knowledge better on. Okay, but is there something beyond that philosophical realm? Okay, chemically, is it going to be important to know the mechanism? Okay, so let's do the first thing. Let's split this and just look at the substitution results versus the elimination results. So elimination. In the substitution, is there a difference between the products? Well, it certainly doesn't look like it. Is there something else that we might need to consider for our substitution? Like that carbon in particular? For instance, that it has 1, 2, 3, 4 different things connected to it. Because we have a chiral product, that substitution mechanism is going to change things. Okay? How is it going to change things? Well, if we look at the SN2, the nucleophile all comes in at the exact same instant, which means I get one possible result. What happens in the SN1 is I form that carbocation. What's special about that carbocation? It is sp2 hybridized. It has an empty p orbital that is above and below the plane. Where can the nucleophile go? It could attack from above or from below, meaning we get two possible products. Okay? So if we evaluated based off of the chirality aspect that we talked about back in chapter whatever it was 5, is this going to be a big deal? Well, the SN1 results in a racemic mixture. The SN2 results in a chirally pure product. Okay? So the SN2 gives you a drug that cures morning sickness. SN1 gives you a drug that cures morning sickness and mutates your babies. Okay? So the SN1 synthetically becomes very questionable as a mechanism. So we want to be able to predict which one is which so that we can set up our reaction to push only one mechanism over another. Similar issues are going to happen with our elimination, though much less obviously, because when we form that carbocation could potentially jump around through a rearrangement, whereas in the case of the E2 and for that matter the SN2, you don't get that jumping around. So it is going to matter as far as our products go. Towards energy diagrams, let's just take a look at our substitutions. If we look at the 1 type where it happened in 2 steps versus the 2 type where it happened in 1 step, 1 step reactant to product. That would be a 2 type mechanism. What about the SN1 where it happened in 2 steps? Well, I'm going to go through and I'm going to form an intermediate and then I form a product. I get 2 humps in this. There's my SN1. So how I would see this manifest in energy diagrams is also different. Okay, so we need to be aware of that difference so that we can appropriately design chemicals and syntheses to make those chemicals. We also want to be able to understand it so that when we look at energy diagrams, we can understand what's happening within those as well. Okay, so being able to identify what mechanism you're looking at is very, very, very important. Okay. To that end, and this you'll notice it says table 9 because it's referencing chapter 9. But as you're moving through this unit, look at each of the reactions that you're being tested on or pushed at, and we'll tell you, do this as SN1. Okay, what I want you to be able to think about is to use this table that Carty's come up with, and I'm going to show you a modified version of it that I like better, okay, and be able to look at it and be like, well, according to chapter 9, that shouldn't happen under SN2 or SN1 reactions. It should be in SN2. Okay? Being able to think to that level is going to be very, very useful much further on down the road, and by much further on, the next chapter. In this chapter, your primary focus is, if I tell you that this reaction runs as an SN1, you do it as an SN1. If I tell you it's an E1, you do it as an E1. Okay? So chapter 8 is a little bit more straightforward. We aren't giving you the freedom to do whatever you want. You do what we tell you to do. Okay? So to that end, let's go ahead and clear all that away, and let's say that this happens as an E1. What product would you expect to get? So first and foremost, you should be able to predict that you need to form a pi bond. You may have drawn that as a product. You could potentially have also drawn that as a product. Okay? How do you decide which one is which? That's the complications that we'll discuss later in this unit. We aren't there yet. As long as you're drawing those two things, I'm cool with it. Okay? What if instead I tell you it is an SN1? Okay? You should be able to go through and add that bromine on there. Note that that is a chiral atom. Okay? Should we be concerned and labeling this as wedged or dashed? Yes, we should be concerned about that. And depending on what mechanism it is, we will be getting one or both of those. So we would have to be aware of those mechanistic steps and those complications that come with those mechanisms. Okay? So, table that I prefer you to use would be this, a little bit bigger so that it covers all of Cardy's stuff. When you go through and evaluate your reactions, start with your nucleophile. If it's a strong nucleophile, that means one thing. If you look at it and you find that it's a strong base, that means one thing. Leaving group, one thing. You'll notice the leaving group is tiny. Why would the leaving group be tiny? Because it doesn't really affect our reaction. All of these reactions are going to require good leaving groups. Okay? So don't stress about the leaving group. It doesn't help you to differentiate the different reagents. After that, we encounter substrate, solvent, and heat. If you go through and look at the YouTube videos I've told you to watch, you'll notice that there's a YouTube video called Nucleophile, which when you watch it, you'll find is tied to base. You'll find one that is labeled as substrate. You'll find one that is labeled as solvent. And you'll find one labeled as leaving group. Those are designed to provide you the basic understanding for each of those individual pieces so that you could theoretically apply into this kind of a table some of that knowledge that you gain as we look at these reagents and reactions. Okay? With that, I'm going to actually backtrack because this next section is all our 152 stuff, and I'll do a brief summary on that if you want it. Okay, so we've got our basic underlying underpinnings for what is necessary for our substitution and elimination. The next video we'll discuss how we would differentiate these according to 152 rates and equilibria, or not equilibria, but rates. And then we'll also move into looking at the actual complications of these. Thanks for listening.